Also, I'm giving some permission to people I know mostly in case you want to ask questions with a microphone. So if you want permission, please let me know before getting started.
Okay, so I guess we can start. Yeah, Sabir, please start your slideshow. And so for the audience, thanks for coming to the last day of the great lecture series by Professor Subir Sachdev. And today, I guess he's going to explain the details and the physical insight behind the Syk model and its gravity duals. So yeah, welcome, and please start, Subir. Thank you.
Okay, thank you, Gil. It's been real fun giving these lectures, and please continue asking all the questions that came up earlier. So yeah, so in the first part of my talk today, I'll give more details of the correspondence I mentioned between the Syk model and a particular type of black hole. I'll try to really show the full calculation as best as I understand it, without putting anything under the rug. And it's useful, I think, to see it just because it's a explicit example of holography. And unlike the usual holography from string theory, in this case, you can work things out on both sides of the dual theory. You can start from both Syk model and from black hole and end up with a common low energy theory. Okay, so I'll begin by first talking about the Syk model and derive its low energy theory. Then I'll start with the charged black holes and then derive its low energy theory. And in the second part of the talk today, after 10 a.m., I will talk about more condensed matter things related to the cuprates. Okay, so let's do the complex Xyk model. And the strategy on the two sides of the duality will be the same. You first just find a suitable saddle point, and then you study the symmetry of the saddle point. That turns out to be the key. You carefully understand the symmetry of the saddle point. And then once you understand the symmetry, then the low energy theory in the usual manner of condensed matter physics, you kind of guess or derive by imposing those symmetry requirements. Okay, so let's do this for the Syk model. And as I showed you in my first lecture, it's a model with these two-body interactions, which are random. That's really the most important thing. It's convenient to take zero mean and have some common root mean square value, but beyond that, nothing else matters. Since this model, there have been many other models studied with much fewer independent elements, and they also have basically the same behavior. The key is that the different matrix elements between the fermions are independent random variables. Okay, so I'm going to pay a bit more attention today to this charge density of the model. Q is a number that goes between 0 and 1. And we'll be interested, close to half filling, where Q is 1/2, but also not exactly equal to it. That will turn out to be important. All right, so this model can be solved, and I'll show at least two different ways of doing it. The simplest way is to just do perturbation theory in U. So you just do perturbation theory in U, and so you can write down all the usual Feynman graphs, and then you average the graphs, average each graph, and you look at how many powers of n are left over after you do the averaging over the U's. So you take the Green's function and just average term by term. And when you do that, you get a very simple set of equations. In the large n limit, there's a self energy, which is just given by this one single graph. So sometimes called the melon graph, because so if you have the generalized Syk Q model, then there's a Q minus 1 line rather than 3 lines, and then it looks more like a melon. Anyway, so this is sigma is just G cubed, where this G is the full Green's function. Okay, so that's it. I mean, so the next the next 15-20 minutes is telling you something about the properties of these equations. This is completely specifies the problem. These, you know, when we first wrote them down in '93, I thought, oh, no problem, we'll solve this in a few days. I think we're still learning. I certainly am learning new things about the structure of these equations even today. There's a lot hidden in them, including, as you'll see, a low energy theory of gravity just in these equations. Okay, so, but one thing you can do, which we did right away, is solve these equations in the low energy limit. At time is much greater than 1 over u. So there's only one energy scale here, which is u. So at times much greater than 1 over u, you can solve these equations. And what you find is that this Green's function, g of tau, falls off with the power law of tau, where this delta is 1 over q, q being 4 in this case. So this is square root of tau decay. Now for a Fermi liquid or a random matrix model with just no interactions, this decay will be 1 over tau. So this is 1 over square root of tau, already telling you that there's something non-Fermi liquid going on here. So this, it also turns out, for the purpose I'm going to discuss today, to also look at allow for particle hole asymmetry. So this is a feature that's not present in the Majorana model, which is particle hole symmetric. So if you have a general charge Q, then the amplitude of this decay at long times need not be the same for positive and negative times, because one corresponds to adding particles, the other corresponds to removing particles. And so, you know, if your Q is close to 1, it's much easier to remove a particle than add a particle, and vice versa when Q is close to 0. So there's an amplitude ratio of these two amplitudes, and that's going to characterize this number E, capital E. And so it's just a number that goes from minus infinity to infinity. I write it in this strange way because it turns out to be a useful way to do things at finite temperature. This E is going to play a crucial role. Eventually, it will become map onto the electric field on the surface of the black hole, on the horizon of the black hole. Okay. Now, one surprising thing. So basically, once you have the solution, what you have then is a realization of a compressible quantum system. By a compressible system, it means that I can just take the chemical potential and continuously change the density in the ground state. And now, if you just think about it, actually the number of examples we know of compressible states of matter is very small, in higher dimensions anyway. Conformal field theory in 2 + 1 dimension has 0 compressibility. You know, like Dirac fermions, they're conformal only when the chemical potential is exactly at 0. And the other compressible states, so the two compressible states we know are Fermi liquids, which are compressible, and superfluids. But what happens in a superfluid is that you've broken the global U1 symmetry, and that gives you compressibility. But this is really one of the first few examples where you don't break the U1 symmetry, and yet you have a compressible state that's not a Fermi liquid. It's really quite difficult to find any other examples. This is really the first solvable example of such a state. Now, one thing we know about a Fermi liquid, that there's a very deep theorem called the Latency Theorem, which relates an infrared property, which is the size of the Fermi surface, to a UV property, which is the total charge. Because, I mean, the Fermi surface is an infrared property because there are 0 energy excitations in momentum space on the Fermi surface. So there's a UV-IR relationship, which in modern language we understand as an anomaly. So it's some kind of anomaly associated with charge conservation and translational symmetry in the Fermi liquid. And that anomaly constrains the UV and IR properties to match each other. Amazingly, it turns out that even in this system, there is a similar anomaly, and that relates the UV property, which is the charge density, which is given by the Green's function at equal time, to IR property, which is E. E is the number here, but determines the long time decay. T tau is much greater than 1 over u. And this relationship is expressed by these complicated looking equations. So this is, looks kind of messy, but in the end, the derivation of these equations is actually has many similarities to the Luttinger-Ward derivation of the Luttinger relation for a Fermi liquid. Okay, so you can continuously tune E, but E, the IR property is connected to the UV property. Okay. All right, so another remark. Yes, please.
So Luttinger relation, I understand it as a mixed anomaly between the translation symmetry and charge conservation, right?
Yeah, right. Yeah.
Do you have such specific anomaly associated with the kind of Luttinger relation for the Syk model?
Yes, it is basically an anomaly associated with charge conservation. There is a discussion in my recent paper, in fact, my only paper with Alexei Kitev and Yingfei Gu and Grisha Tanopolsky. So there's a section in that paper where we discussed why it looks like an anomaly. Yeah.
I see.
Yeah.
Okay, thanks.
But there's another derivation in this paper, which is when we originally found this relation, which is very similar, the usual derivation using the Luttinger-Ward functional.
And there is another question from Joseph Hoy. Is the tau bigger than 0 expression is maybe minus tau to the power or minus tau to the power? So maybe it's better for you to, it's about typo, I guess.
I don't believe there's any typo.
Okay, I think, yeah.
This is just, it is negative.
Yeah.
And this is, they do have opposite signs.
Right. Okay.
I think this is fine. What I should have said is tau not just greater than 0, tau much greater than 1 over u. And this is mod tau much greater than 1 over u. I didn't say that. But I think this is correct.
Yeah, I think, yeah.
Okay.
Yeah, thanks.
Okay. All right, so another remarkable thing, which is actually a property of just these equations. We didn't realize this in 93. If you just look at, so I showed you the solution of the equation at 0 temperature. It turns out these equations, and I'll show that in a few minutes, have a conformal invariant structure. And because of that, you can get the solution not just at 0 temperature, but at finite temperature by a conformal mapping. So once you know the answer at 0 temperature, which is this one, then as long as temperature is also much smaller than u, then you can get the answer at finite temperature. And this has the kind of sine tau function that you may have seen in 1+1 dimensional conformal field theories. Here, curiously, we have a 0-dimensional system, which is random, and yet generically it has a conformal type low energy response function. Okay, so you could now take the Fourier transform of this and then compute the spectral density, and these are the kinds of curves you get. So this is a function. So various interesting features at large frequency, it decays at 1 over square root of omega. But at small frequencies of order kt, it's a universal function of omega over t. So that's the Planckian scale of everything. And then it has the peaks at positive or negative energies, depending on the particle-hole asymmetry. So for example, if your Q is less than a half, then it's much easier to add a particle, and that will, I think, correspond to the blue line, and vice versa for Q greater than 1/2. All right. There's another very important property of this model. So now, at this point, we've got this 1 over square root of omega decay, and you say, oh, this means there are no quasi-particles. But that's a bit quick, because what this tells you is that the electron, your bare particle, is not a quasi-particle. But there could be other particles. And in fact, that's what happens in a Luttinger liquid. A Luttinger liquid, it's true that if you look at the electron spectral function, it's non-Fermi liquid-like. But ultimately, the Luttinger liquid is the theory of gapless bosons, free gapless bosons. And there are quasi-particles, they're just free gapless bosons. So maybe there is some other non-local operator here, a very complicated non-local operator that we are too stupid to figure out, which behaves like a quasi-particle. Maybe somebody's going to solve this model and see it's integrable or something in some other variables. That's kind of the question. Is there such a thing? We don't. So 1 + 1 dimensional CFTs usually is such a thing, but in higher dimensional CFTs, we don't believe there's such a thing, and neither, in fact, are giving no evidence that even this model is more like a higher dimensional CFT than a low dimensional CFT. So one way you can see this is by computing the entropy. So this is an argument which was in the paper with George and Parcolet, which tells you, this is sort of an argument that allows you to figure out the temperature depends on the chemical potential. So if you have a fixed charge and you raise the temperature, how does the chemical potential depend on temperature? Now, this is a calculation you do in solid state physics for Fermi liquids, how the chemical potential depends on temperature. It's a very standard calculation, and by the Sommerfeld expansion, and you get some T over EF squared correction. Okay, so there's a calculation you can do, which the steps are outlined here. I won't say more about it, but it gives you at the end this very general result, where the chemical potential at a fixed charge depends on temperature in this way. Rather than having a T squared dependence, it has a linear in T dependence. In a Fermi liquid, this would be T squared. And the coefficient is exactly this number E, this particle hole asymmetry. And it turns out that if you look at a charged black hole at fixed charge Q, this is also the way the chemical potential depends on temperature, as we'll see in a minute. Okay. Now, once you have this rather strange dependence of the chemical potential on temperature, then immediately you can deduce some very interesting things. So this is another way to say it, that d mu dt at fixed Q is this number E again. And then you have a Maxwell relation. Go back and remember your stat mech. D mu dt at fixed Q is the same as ds dq at fixed T. Okay. That just follows from the fact that mu and s are conjugate variables and some free energy. Okay, so that tells you that ds dq, this is how does the entropy depend on charge at a fixed T, is non-zero. And that's quite a remarkable result, because this tells you that even at zero temperature, the entropy in the limit n goes to infinity first, and then T goes to zero, is not zero, because it's got a non-zero derivative as a function of charge. So from this, you can compute the entropy, and you get some number. So it tells you that this entropy as T goes to zero at fixed n, at n goes to infinity, then T goes to zero is some number S0, which you can compute. You can get the exact value of that number from this argument and the Luttinger relation. Okay. And also, this is true then, that ds dq is 2 pi e. I've already said that. And integrate this to get S0 as a function of q. So if you do that, how does that give, what does it give you at S0 at, say, q equals 1/2? Well, you just integrate from q equals 0. And certainly at q equals 0, it's an empty system. The entropy has to be 0. You just integrate that. You know how E depends on Q from the Luttinger relation. And you get this bizarre number of 0.46848. That is the entropy of this SYK model at half filling. Okay, so what does this mean? Well, what I've plotted here is a numerical result. You take 12 sites and you look at all the states. So there's 2 to the 12 states. Okay, this is the lowest energy state here, and that's the highest energy state there. So the width of this is the number of, it's quite easy to see, is n times u. But the number of states in here is 2 to the n. since I'm looking at all, I'm not conserving Q. So you have 2 to the n states in a width of order n, which means that the level spacing, to exponential accuracy anyway, is 2 to the minus n, or e to the minus n log 2. So that's how many levels you have very close to each other here. So what does this entropy tell you? This entropy tells you that the level spacing down here is almost the same as it is in the middle of the band, right? It's equal to the e to the minus s naught, and s naught is slightly smaller than log 2. Not slightly, I mean, it's okay, 30–40% smaller than log 2. Of course, 12 is too small a number. You can't quite see that it's pretty dense here. But if you take a integrable system or something like the random matrix model of single particles, you'll find the energy level spacing down here is much larger. In fact, typically any system with quasi-particles, the energy level spacing here is about a 1 over n, not e to the minus n. And that's because when you have quasi-particles, there's some lowest energy quasi-particle excitation, which will have energy level spacing 1 over n, because you're solving kind of a single body problem. And then you get the many body states by adding many different quasi-particle excitations. So at low energies, all the levels will be of order 1 over n, although eventually they become much closer spaced when you get to a finite energy density. And so the fact that you have so many energy levels down here tells you that there is no quasi-particle basis. And that's really ultimately the strongest argument that this system has no quasi-particles because of this dense level of spacings down to 0 energy. Yes, question. Unguk. Please go ahead.
So with this structure, if I measure specific heat,
yes,
temperature, can you comment on temperature dependence and low temperature?
So this result can't tell you what the specific heat is, so we did not compute it. The specific heat requires the calculation I'm going to do now, and that was first done by Kitaev. And what he showed was that specific heat is linear in temperature, so it's just like a Fermi liquid. There's a gamma coefficient.
So this gamma
to see the entropy, you have to integrate the specific heat. So if you do an experiment, you really won't see any sign of this entropy. It doesn't lead to any singularities. Okay. All right, so that's the mean field theory, the saddle point, and its remarkable properties. All of those properties we already knew by 2000. Nobody seemed to care, so we kind of didn't work on it too much. Anyway. All right, so now let's go beyond the larger limit and try to think about more than just the mean field saddle point and the structure. And the key thing here is this understanding of the symmetries of the saddle point. So these are the same equations I showed you earlier. Here Z is a frequency space. Now you can see here that at low frequencies, the solution is such that this frequency dependence here is square root of omega, and that's much larger at low frequencies than the I omega. So at low frequencies, in the limit we're interested in, you can just throw out the I omega term, and this mu will cancel with sigma of 0. In fact, it has to, otherwise there is no solution. So if you throw those terms out, then these two equations, it's very suggestive to write it out this way. These are the equations we're solving. Sigma g equals 1, and then sigma I equals g cubed. Okay. And these equations are where I think of the sigma and g as bilocal fields. They're not, of course, the solutions that we're interested in, they only depends on the difference of the times. But if I take them as general functions of 2 times, then these equations have a huge amount of symmetry. And that was pointed out by Kitaev. So here this
Subir, before you proceed further, the Seokbam Chang from University of Seoul has a question.
Yes, please.
So you can speak up, Seokbam.
So it's from the previous slide where you showed us the structure of the spectrum. So, I mean, if you add in one particle hopping to this
Yeah.
SYK Hamiltonian. I mean, how would that change the structure of the spectrum, and would that cause the just this zero temperature entropy to just go away?
Yes, it does. So basically, at low energies, the level spacing become 1 over n. Yeah, it becomes integrable, effectively integrable at low energies.
I see.
But if you add anything else, nothing will change. It's totally robust to everything except that one term.
I see.
Yeah. I should say, so we got this result, this number, I said in 2001, but there was no way of checking it because you couldn't. The original model we were looking at was too hard to put on the computer. But with the Kitaev version of it, it's trivial to put on the computer. And there's, of course, much better results than this, up to 30 sites these days, I think 30 even greater. And there's very precise numerical checks of this just by looking at the level densities. It's correct. It works out. Okay. All right, so now I was going to talk about the symmetries of these saddle point equations. So what Kitaev pointed out, that it's invariant under time reparameterizations. If you think of these functions as functions of 2 times. Ignore the little g here for now. So if you go from time tau to time sigma, and at the same time put in these scaling factors in front of sigma and g, you get a new theory of g tilde and sigma tilde, and these 2 functions in the new time will obey the same set of equations. There's actually a further symmetry. There's even an emergent gauge symmetry that's associated with little g. That's what I pointed out. And that plays a role in looking at the nature of the charge fluctuations. Okay. Now, this seems like a huge amount of symmetry, and you seem to have many, many, many solutions. But the point is, most of those solutions are not sensible saddle point solutions, because any sensible solution should be a function of tau1 minus tau2. And in general, you can just see from the structure of this transformation, even if if G is a function of tau1 minus tau2, G tilde need not be a function of sigma 1 minus sigma 2. So most of these G tildes are, totally useless, at least for the saddle point. But as we'll see, this symmetry is very important for the fluctuations about the saddle point, the structure of the fluctuations. In particular, choosing an f of sigma that maps the line to the circle, you can get the finite temperature result that I showed you earlier. Okay. All right. So let's actually pick the solution that we have found. This is the solution that we found. Tau1 minus tau2 goes as 1 over square root of tau. That's what GS is. Okay, so now we ask the following. Let's make this transformation and get a G tilde. And I ask the following question: for what transformations f of tau is G tilde have the same form as GS, the original G? So this is very similar to, for example, let's take a spin system which has O3 rotational symmetry. And then you find a ground state where it's a ferromagnet, the spin's pointing up. And then you ask, what's the symmetry that's left over? Well, there's the symmetry of rotation this way, that's broken. But there's a symmetry of rotations about this axis, which is still left over. So your SO3 is broken down to U1. So here you have a diffeomorphism symmetry. And what is left over at the physical saddle point? Well, so what f of tau will give you a G tilde, which has the same form as G. And it turns out it's these fractional linear transformations. The group SL2R are the set of transformation which leave the ground state or the vacuum of the system invariant. Okay. Now, so you could say this is a system where you've broken reparameterizations down to SL2R, but that's not, again, a totally precise statement, because the theory doesn't really have reparameterization symmetry, and the action doesn't, as I'll show you in a minute. It only has that when you ignore these terms, and these terms have become important in the UV, but they're not important in the IR. So there's it's not really like a ferromagnet with full rotational symmetry. It's like a ferromagnet which has some higher gradient terms that break the rotational symmetry. So sometimes these terms are called dangerously irrelevant in condensed matter. Anyway, okay, so that's the analysis. Yes, and you can let me just finish the statement. And this symmetries can also be extended to finite temperature. Yes, please go on.
There's a question from CP. Yeah, you can unmute and speak up. Okay, maybe the person who raised the hand is not there.
Okay.
Maybe absent. Yeah, sorry. You can go on.
All right. All right. So now let me show you. Let's write down what's now called the G sigma approach. I learned this. We did in 2001. We did this by a slightly different approach using more conventional Hubbard-Stratanovich tricks in condensed matter. And then I learned this G sigma approach that particle string theorists like Maldacena seem to use. And now I'm finding it very useful in all kinds of condensed matter problems. It's a really nice way to do things. So how do you proceed? Well, you write down the path integral for the Syk model. So the first approximation you make, which has now been numerically checked, is that you just average the partition function rather than averaging the free energy. What this means is you're assuming the system self-averages. And in fact, it absolutely does. We have a lot of numerical evidence that it does self-average. Okay, so you just average the partition function, and this is what you get. Now you insert 1 equals this. So this is a path integral over 2 bilocal fields where G and sigma are now actually your variables of integration. They're going to become your degrees of freedom, and they're not necessarily functions of tau1 minus tau2. There's an integral over all of them. This is why it was useful to consider the bilocal fields earlier. Okay, so this is kind of a obvious statement. This is 1 is equal to this because if you do the integral over sigma, it gives you a delta function of G, and do the integral over delta function, you get 1. And this tells you that G is equal to the Green's function, because when you do the integral over sigma, you get a delta function. G is equal to CC dagger, minus CC dagger. Yeah, somebody is raising their hand. Please go ahead. Okay. All right, you put.
Yeah, sorry. Do you have a question?
Okay.
Yeah,
so you can just put the 1 inside the integration, and then what happens is that you can just replace this C by this G. And once you have done that, it's just a quadratic integral over the C's. You can do the C integral. And so at this point, you have an exact representation, assuming self-averaging, of the partition function of the Syk model. So this is what it is. It's got 2 bilocal fields, G and sigma, of tau1, tau2. And this is the exact action with no approximations so far. So you have to, this integral has, the log det of the inverse Green's function, and then this is the thing sigma G. That was the term that was over here. Oops, that's sigma G over there, and this is the interaction term proportional to U. Okay, so that is the full theory. I could have just pulled that theory out of a hat and say I'm studying this theory. Okay. All right, so now you could just start with this and look at the saddle point, and the saddle point equations will be exactly the equation I showed you earlier. And then you can also see this whole path integral has these symmetries in the limit where you ignore this d by this term over here, this delta function term here. Okay. All right, so let's assume you found the saddle point, and then you look at the fluctuation about the saddle point. You get some horribly complicated action. Not that complicated, but anyway, now you want to do this path integral. So this is nobody knows how to do this integral. This is way too complicated. It's a big parameter space of 2 bilocal fields. Sorry, that should be a tau 2. However, what we're going to do, so we're going to look at the action, and the action, has many different directions. This multi-dimensional space, but there's one direction where the energy doesn't change very much. And what is that direction? Well, that's the direction in the space where you do the time reparameterization, because we know that the low energy action doesn't change as you do a time reparameterization. Okay, so instead of integrating over G and sigma, we're just going to integrate over f of tau, where G, the variable of integration here, this G, is replaced by an integral over f, where in the action, what is the dependence of the action on f? Well, it's basically the time reparameterization of the saddle point. Okay, so this is very much like integrating over metrics. There's also a gauge symmetry, so you also have a phase that you want to integrate over. And there's some constraints between the two that I haven't described related to the ds dq equals 2 pi e relation. And therefore, you can approximate this path integral over 2 bilocal fields to this path integral over 2 local fields. This is just quantum mechanics in a sense of f of tau and phi of tau with some effective action, which you just obtain by inserting this in there. Okay, that's the it's a principle of this. Once you realize that this is the proper low energy direction, is relatively straightforward. And this is completely the analog in a ferromagnet of saying, well, I've got the state here, and then when I do the low energy theory, I should just sum over the Goldstone modes and forget about everything else. Forget about, say, amplitude fluctuations of the ferromagnetic moment and so on. Okay. Now, this is still too hard. If we want to get what S effective is, putting this in here and evaluating that is not so easy. But you can almost guess the complete answer by symmetry. Just like in a ferromagnet, you can write down the nonlinear sigma model just by a guess. So you do a similar guess here, and this turns out to be the answer. This is the term that we obtained, but this is the term written down by Kitev and Maldacena and Stanford. It involves, ignore the tangent. Let's just imagine we're at 0 temperature, but it's just replaced by f of tau. So it's what's called the Schwarzschian of f of tau. And it's some complicated set of horrible derivatives that I've never seen before, at least in condensed matter physics. And so why does it have this very complicated form rather than just grad f of tau squared or something? Well, the point is, whatever this effective action is, it must be the case that if you do just rotate about the axis, that is, other words, if you do an SL2R transformation, where G goes back to, so if this transformation f of tau is SL2R, GS doesn't change. Okay, so that's also true here. When I'm doing this transformation, if f of tau is SL2R, G is just equal to GS. And so you're not actually even moving away from the saddle point. So it must vanish for SL2R. And this Schwarzschian function is the simplest function which vanishes for all f of tau. Okay, so therefore you got to have that, and then the only thing left over is to compute this coefficient. And this coefficient is called gamma, at least by me, because that's the gamma value of the specific heat. It turns out the specific heat of the system, when you evaluate this at finite temperature, is gamma T. It's very much the analog of the gamma T coefficient of a Fermi liquid. And this part is related to the compressibility of the system. Okay, so that's the effective action. Getting gamma requires some numerical work if you want to get the exact value, or you can do it in some additional expansion parameters. Okay, so this might look like a very horrible action. Sorry. Well, I guess I rewrite it here. This looks like a very horrible path integral. In particular, it's got these horrible derivatives, and it with 3 derivatives looks totally unstable. But in fact, this path integral is perfectly well defined. You can evaluate it. In fact, you can evaluate it exactly. The first shown by Witten and Stanford, how you can do the integral exactly. It's and the reason it's well defined and why these infinities are fake is because when you do the path integral, you have to mod out by the symmetries. So, you know, in a ferromagnet, you have a symmetry of global rotations. Here you have symmetry, sorry, of U1 rotations of a ferromagnet. Here you have the group SL2R. Now, for a ferromagnet, this rotation is not, doesn't worry you too much because it's just a fine, you know, it's a compact rotation and it's just an overall factor in front of the partition function. But here it's more serious because the group SL2R is a non-compact group. So you have to mod out the path integral by the volume of SL2R. And when you do that, everything is perfectly well defined. Okay. All right, so that's the main result. The fluctuations about the saddle point that we found in 93 are given by this partition function. The leading term is the zero temperature entropy, and this gives you temperature corrections to various things from, and you can also do better by looking at higher other irrelevant operators, but the leading irrelevant operator is this time parameterization.
Yeah, there's a question from Unguk.
Yes.
So this gamma is probably functional of your coupling constant U.
Yeah.
And charge.
Correct. Yeah. So we have to do that numerically. We don't know. We don't have an exact result for it.
So in usual condensed matter system, we judge this. So the system is whether a heavy fermion or just weakly correlated system by considering gamma. Do you think which category is more closer in this case, or can you judge using gamma?
Well, normally gamma is the effective mass of the quasi-particle, right? Here there are no quasi-particles, so it's the analog of some quasi-particle mass. But I'm calling it gamma because it appears in specific heat. But it's really, as you can see, in this case, associated with these time parameterization fluctuations. But time, you know, as you know, time parameterization is dual exactly to the stress energy tensor, or energy in this case. So gamma controls the energy fluctuations, and that's what gives you the specific heat, right?
Okay.
But the fact is, but it is quite remarkable that you get a linear NT specific heat.
Yeah.
We always thought of linear NT as a property of a fermionic system, but here you have a bosonic path integral that gives you linear NT. Yeah.
I also have a naive question. So you said that because of the reparameterization symmetry, there are many solutions, even though we are interested in only one case where tau 1 minus the Green's function is proportional to the tau 1 minus tau 2. And the solutions generated by PSL2R. So other solutions, are they simply unphysical, or is there any physical interpretation for them?
Well, if I'm thinking of the saddle point, if all I did was a saddle point, and this is probably why we never thought of this in the old days. If you're just thinking of the saddle point, it seems unreasonable to think about solutions which depend on 2 times.
Right.
The symmetries only appear when you have a treat of this G as a function of 2 times. Okay. So at this level, they look totally unphysical. But what I've then shown you by this G sigma trick, I have now a path integral.
Right.
So now in the path integral, it's absolutely required that this be a function of 2 times. That comes from the structure of the action. You can't make this. It's not a path integral over G of tau 1 minus tau 2. It's a path integral of G of tau 1 tau 2. So for this path integral, those, if you wish, are not saddle point configuration, they're off-shell configurations, which I have to integrate over. Right.
I see.
And the reason it's a bilocal path integral, I mean, this really goes back to why is there 2 times? So if you ask why are there 2 times, that goes back to this thing. When you do the disorder average,
Oh, good. Yeah.
you get the 2 times here, d tau prime.
Right.
That's why everything becomes bilocal.
I see. Thank you. Yeah.
So yeah, so there was also some work actually by Jinu Ye and Nikhil and myself on random spin glass models in those days, where we had all these bilocal path integrals that we were able to evaluate. And then when we wrote down SYK, I started thinking a little bit about, well, what's the appropriate bilocal path integral, but I didn't make too much progress. Okay.
Thank you. Yeah, thank you for clarification. Yeah.
Sure, a good question. All right, so that's the end of the main result for the SYK model, this path integral. Okay, so now let's go to the second part. We're going to detect charged black holes, and here our theory would be just the Einstein-Maxwell theory. We look at the saddle point. This has, of course, been known for a while. And then Hawking told us that once you have any classical solution, what its entropy is. That's why I'm calling it the Einstein-Maxwell-Hawking theory, because Hawking just tells us it's the area divided by 4 in appropriate units. So you can just solve the solution and then put in the H bar as Hawking tells us. But here we'll be, in fact, go beyond that. We'll look at the path integral of fluctuations around the Einstein-Maxwell saddle point. Okay. All right. So I guess I showed this 2 days ago. There's a charged black hole solution which have the feature that as you approach the horizon, the metric along this direction and this direction factorize. So I'm going to show that here more explicitly. So let's start with, so here's our theory. We'll put little d equals 2. I've written in general d. So this is the Ricci curvatures, Ricci scalar, sorry. This is the Einstein action. Kappa squared is the Newton constant. This is the cosmological constant, which we take to be slightly negative, but you can make it as small as you want. But it's good to have some slight negative curvature to control the UV behavior. And this is the Maxwell action. Okay. So our degrees of freedom are the metric and the gauge field. And we have to now impose some boundary conditions. So we're going to impose a boundary condition that you go out to infinity. The solution is just the ADS solution, which you get with a negative cosmological constant. So it's almost like Minkowski space as the curvature as L goes to infinity. And there's some net electric field going out. So there's a net charge somewhere in the center. Okay, so with these boundary conditions and these equations, well, you can solve them. And I hope you believe me that I actually did solve them, but I used various Mathematica programs that tell you how to solve these equations once you have this information. And once you have the solution, then you want to go to the path integral over the metric and the gauge field for this thing. Okay. Now, of course, this path integral is totally meaningless. It's full of all kinds of infinities. It's why we invented string theory in the first place, because no one knows how to do such path integrals over gravity. However, so this might seem like a totally hopeless task. However, it turns out that if you focus in on just the low energy sector of these charged black holes, this path integral can be done, and it gives you a precise number. And it's kind of amazing that this wasn't discovered earlier. This could have been discovered, 30, 40 years ago, but it wasn't. And one could speculate why, but it's curious. It's only after the connection to the SYK model was uncovered that people thought of looking at this path integral and making sense of it. Okay, so here's the action again, and here's the solution. Okay, the details don't matter very much. So basically all the parameters in the solution can be determined in terms of the boundary condition and the Hawking temperature, the charge Q and the Hawking temperature. So all these numbers can be determined. Let me just show you. Yeah, so this is more details with various numbers near what happens near the horizon. Let me just show you the picture here. So this is the important picture. So if you take this metric and look at its behavior right near the horizon, then what happens is that it's AdS2 cross S2. This is the S2 part, and this is the AdS2 metric. There is an electric field coming out, and the strength of the electric field is just given by Gauss's law. The net charge inside must be, Q, and so that determines E. Okay, so the same number E, and as we'll see it, this plays the same role. In fact, if these solutions, if you compute d mu dt, which was 2 pi E, that's exactly what you'll find here. Furthermore, also, since the Hawking theory of thermodynamics of black holes obeys Maxwell's relations, you also get the Bekenstein-Hawking entropy with respect to Q is 2 pi E. So this comes out from Einstein's equations, amazingly, and the Hawking extension thereof. And so I have, in my life, I have derived this equation first using Schrödinger's equations for the Syk model, and then next using Einstein's equations. You get the same equation quite remarkably. All right, but now we understand why. It's again related to symmetry. All right, so that's the saddle point. Now we want to look at fluctuations. And the strategy is exactly the same. What is the symmetry of the saddle point? So now we are asking under what metrics, under what space-time transformations does the metric remain invariant? You have a saddle point, so it's an integral over metrics. The saddle point is AdS2. Under what transformation does AdS2 go back to AdS2? Well, amazingly, that's SL2R, the same group that we met in the Syk model. And that's really the key to why the two theories are the same. And so I invite you to check that this metric, which is now written in Euclidean time, and Euclidean time, this is the metric of hyperbolic space, the space of constant negative curvature, first found by Lobachevsky. And you can just check that this metric remains invariant under this transformation. It's kind of fun to do that, and it does work out. Okay, so when I'm doing the path integral, I have to mod out by SL2R, which is an infinite group, and it turns out that's enough. That will get rid of all the infinities. All right, so that's the symmetry here, but this symmetry of SL2R and this AdS2 structure does not survive at far from the horizon, or in other words, at higher energies. At higher energies, the metric becomes AdS4. So you go from a 2-dimensional spacetime to a 4-dimensional spacetime. And so what are the path integral, it turns out, is just dominated by that in the boundary. And roughly speaking, why is that? Well, it's because in 2D gravity, there's no graviton. You can always gauge away the graviton-like fluctuation as fake coordinate transformation. There's no invariant graviton. You don't get a graviton if you just try to look for it in 2D gravity. So the actual physical fluctuations are almost all completely gauged here, and the only real fluctuations that contribute to the partition function are on the boundary. Okay. So there's a calculation you have to do now, which is you start from Einstein-Maxwell theory, and then you found the saddle point, and you look at the semi-classical fluctuations around it in the low energy limit, where you only focus on these boundary degrees of freedom, far from, as you go from the near horizon region to the far horizon region. All right, so I first saw this calculation or a version of it in Maldacena and Stanford and Yang. But there's a very nice couple of recent papers by Eliasiu, Turiachi, and a couple of other people, which really go into this in great detail, not just for Einstein-Maxwell theory, but also for various supersymmetric black holes. And this turns out to give the same procedure applies there too, and gives you, corrections to the entropy that had been obtained earlier by string theory beyond the leading large N limit. Okay, so the basic idea is here. So you have a metric in 4-dimensional space-time. You write that metric as a 2-dimensional metric, which is the transverse, the spherical metric. So here I'm ignoring angular fluctuations. This paper includes them too. And then there's the, sorry, this just, excuse me. This is the angular metric, and it has a coefficient we call phi squared. This packs for phi is for convenience, and the 2-dimensional metric is a dynamical degree of freedom that we keep in general to be anything. Okay, so it turns out that there's another parameter phi that you have to introduce. So when you dimensionally reduce from 4 to 2, you get a scalar field phi. So now if you insert this ansatz into the Einstein-Maxwell action, which is in 4 dimensions, you get this 2-dimensional theory. And this theory is now called JT gravity. It's one version of JT gravity, where you have a 2-dimensional Ricci scalar and a scalar field phi. So a scalar field automatically appears to make 2D gravity non-trivial. Okay, and now you look at this JT gravity and look at its fluctuations along the strategy outlined by Maldacena, Stanford, and Yang. This is something I went through in this paper just for my own satisfaction. And then what you find when you go through this analysis, and I'm going to just skip over it because it's kind of technical. But at the end, what you find is exactly this Schwarzian action for this f of tau, where f of tau is basically the coordinate of the boundary of ADS2. So you choose the boundary of ADS2 at coordinates f of tau, zeta of tau, where zeta is related to f of tau. By this, to make sure the metric remains, you put in a diffeomorphism invariant boundary condition, and you just evaluate the action only as, so this is sort of like fixing gauge. I mean, this calculation is, not that different in principle from what we do in condensed matter, where you do some slave boson calculation, you find a saddle point, and then you look at fluctuations, and provided you parameterize it properly, the fluctuations are given by some Maxwell theory or Chen-Simons theory or something. So we know how to do that. It requires some skill, but in the end, it's just a matter of finding the right variables. And this is in principle exactly the same thing. You have an action, you have a saddle point, you just find the right low energy variables. And the correct low energy variables turn out to be just f of tau, modulo SL2R. And that's why, in fact, for the same reason, the action is the Schwarzian pops out. In this case, actually, you can derive it. You don't have to guess it. And I had a lot of fun going through this calculation and seeing out puffs the Schwarzian, exactly this thing. All right, and now you have a coefficient gamma. In this case, gamma is related to Newton's constant and the electric charge of the black hole. You can work it out exactly. All right, so that's the main result. You can also now do that for the phi that comes from the gauge field, and you get exactly the same theory. So this is the main result for the black hole. This is the low energy theory. This is the Bekenstein-Hawking entropy. And then this Bekenstein-Hawking entropy obeys this magic relation, which also is obeyed by the SYK model. And so this S effective here for the SYK model is exactly the same as this. No difference. And the very, very different calculations that I've kind of outlined, showing you how you get that. All right, I think that's all I have to say for the first part of my talk. So we'll break for a few minutes then.
Yep.
I'm happy to have questions too.
Is there any question from audience? Then maybe we can, go on.
I have one question. So whatever you do, so when you get is just the same effective action. So whatever gravity, you start, maybe this is just maybe special.
No, as long as you have I believe it'll happen for anything, as long as you have an ADS2 metric, ADS2 cross whatever at low energies near the horizon. The ADS2 is the key thing. because the ADS2 has the SL2R symmetry, and that pretty much demands that the action be this form.
And also another question is, while I mean the starting from higher dimensional gravity
Yeah.
itself is making sense, but there is no point of extending Syk model itself to higher dimensional case, right?
Yeah, no. So the higher dimensional, it's just a nice, just shows you how general this theory is. I mean, in principle, you could just start from JT gravity as your theory and show it's related to Syk in the low energy limit. I mean, Syk has many more degrees of freedom than JT gravity. But nowadays, I mean, as you know, so many people are studying JT gravity on its own. But JT gravity on its own is not really a quantum theory of anything, but it's an average over quantum theories. Whereas the Syk model or given sample is a perfectly well-defined quantum theory.
So do you want to claim that there is a certain kind of universality that, for example, all sort of, I guess, a trial is eventually reduced to this universality class? And what kind of physics is really encoded in this universality?
Well, I think, yes, there is a universality class. And on the gravity side, as I said, it's basically any theory whose low energy limit has an ADS2 factor. I mean, ADS2 on its own is nothing because you need to embed it. It doesn't have any real degrees of freedom. You need to embed it in something. You need to either add a scalar field or embed it in a higher dimension. But all of the, I believe all of the string theory exact computations of Bekenstein-Hawking entropy also use ADS2. It's all for ADS2. And so this calculation, this universal Schwarzian, and for supersymmetric black holes is a super Schwarzian, gives you the first correction, the leading low temperature correction to the entropy that you computed in string theory also for all the string theory black holes. That's been discussed very nicely in this paper by Iliescu and Turiachi. Yeah, this one here.
Okay.
Yeah. Yeah. Yeah, I mean, it's again, in principle, after Strum and Javafa had their famous calculation of the black hole entropy, you could have asked, what are the corrections to the thermodynamics at low temperature? And for some reason, in principle, a long time ago, people would have thought of the super Schwarzian and worked it out, but it wasn't done until recently.
So actually, I thought that this ADS2 is a consequence of looking at zero temperature limit. But by looking at this ADS2,
well, ADS2 is conformal to, you can also go to finite temperature. There's a version of ADS2 at finite temperature that you can find in this paper. I mean, that's well known. It's nothing new.
I thought that ADS2 is a consequence of the, the critical. That means T equals 0 behavior.
Yeah, so it's, but okay, conformal to ADS2. There is a conformal form at finite temperature. There is a transformation. Okay, I don't know. Yeah.
Okay.
I have the metrics are written down in various places at finite temperature. So yeah, I mean, it is a critical state. Every black hole is a critical state. I mean, if it wasn't, it would have quasi-particles, and that's not possible.
Okay, then maybe we can move on to Vladimir.
Yes, hi, Subir,
Hi,
fantastic stuff. Hi,
thank you.
This is so exciting, but what I didn't quite understand is on the condensed matter side, this is an infinite range model, and it's a kind of mean field theory.
Well, I mean, yeah, it's it's the full solution of this model, including 1/n corrections. So speaking to you, I would say, it's kind of like a DMFT or eDMFT solution. But now we are understanding how to do corrections to eDMFT also for the critical non-Fermi liquid solutions of eDMFT. That's what SYK is. For these non-Fermi liquid solutions, we know not just the saddle point, but we know how to generalize to finite temperature. We know all the spectrum of operators. We know the path integral in certain sectors exactly. And this is, I'm finding it very useful for many condensed matter problems these days. So,
Okay.
You're
so,
muted, Vlad.
Yeah.
Okay.
Yeah, maybe we can take 5 minutes. I would like to give Subir great thanks. And let's give him 5-minute break so that we can hear last lecture, which I'm really looking forward to listen. So, yeah.
Okay, thank you.
Yeah.
All right, see you soon.
Yeah. Yeah, so for Korean audience, I'm going to start 10:13 or 10:15-ish. And yeah. So for ET, I think it's 8:15-ish. Yeah, 8:13 or 8:15-ish. Sphere, when you are ready, you can slowly start. Yeah. If you wish to take one or 2 more minute break, that's fine. But when you are ready, you can. Yeah.
Yeah, no, I'm ready. So
yeah, then maybe you can start.
Okay, so you see it all right?
Yes.
Okay, so I've changed the title of my talk somewhat from what I announced earlier. So I'm going to return to this famous phase diagram of the cuprate superconductors. You know, one could could have whole, you know, many conferences and thousands of papers written on different aspects of this phase diagram. And people still disagree somewhat on what the significant things are. So what I want to do today is just begin with what I think is the key important problem here, which is largely open, that we really need to understand. And this really has to do not so much with the superconductivity, but with what's going on here between these 3 different metals, the pseudogap metal, the strange metal, and the Fermi liquid. Okay, so let me emphasize what is this, so let me just, among the thousands of experiments, let me just highlight a few important, what I consider to be the important and also very recent experiments. This is not so recent. So one property, if you look at high doping at large P, you see what's called a large Fermi surface, where the volume enclosed by the Fermi surface is just given by the usual Latency theorem. On the other hand, if you go to low doping, that large Fermi surface seems to disappear around some critical doping. So it's not quite clear what photoemission is seeing. But there has been a more definite claim in a recent angle-dependent magnetoresistance measurement. So the difference between ADMR and photoemission is in ADMR, you're not actually knocking an electron out of the sample. So if there is some quasi-particle, even if its spectral weight, if its overlap with the bare electron is very small, it will show up much more clearly in this new experiment. It could just be that, you know, there is a quasi-particle, but its overlap with the bare electron is so small, and that's why photoemission doesn't see it. Anyway, so this ADMR experiment finds, again, the same difference between the large P greater than PC, where you have a large Fermi surface very clearly, to P less than PC, where they tried various models, and this model of whole pockets of volume P fits the data best. Okay, so there's this Fermi surface transformation between small and large doping. So that's important property number 1. Another important property, which is highlighted most clearly again by another experiment by the same authors, where they looked at from the ADMR, they tried to reduce the scattering time of the quasi-particles around different direction. And they found both an anisotropic and an isotropic piece. And the isotropic piece is perfectly linear in temperature, 1 over tau, with a coefficient of order 1 or 1.4. And both of these behaviors are, you know, quite universal. All right, so there's some kind of Planckian time dynamics, at least in the isotropic part of the scattering rate. So then you can also ask what happens as P goes through PC. Well, there's a peak in the specific heat, the gamma value of the specific heat, the same gamma we were just discussing for the SYK model. And finally, I want to mention also a fairly recent experiment by NMR, by Marc-Henri Julien, looking at the underdoped side and claiming that at least in a high magnetic field, there's pretty good evidence for some kind of spin glass state all the way up to the critical doping. All right, so those are the experiments I've highlighted, and this puts up a challenge. This is what I think we really need a theory for. We need some model that will display this behavior. We need a transition from a small Fermi surface to a large Fermi surface, a single band model where there's some kind of Planckian behavior near the critical point. Okay. So that's the challenge that I want to address in this talk. what I'll give you evidence for that there is a very simple model that at least has all of these features and more. We don't fully understand that model, but it has some connections to SYK physics too. All right, so I'll define that model and present its numerical solution. This is very recent work with Henry Shackleton, Antoine George, and Alex Vitek, these two gentlemen at Flatiron Institute. And then some analytical work by my students, Maria Tikhanovskaya and Hayo Guo, and postdoc Grisha Tarnopolsky. Okay, so this is the model that we are going to study now just by exact diagonalization. So it's a TJ model, which is the model we want to study. And I guess I mentioned this in my first talk. We're going to make a rather drastic simplification, which is take Hij and Jij to be random numbers. So there are 3 states at each side, empty, up, and down, and these are random numbers. So if you want to see a picture, there's some bunch of sites with a bunch of electrons with the spins in different orientations, and the electrons can hop from any site to any other site with a random number t, and exchange spins between any pair of occupied sites with a random number j. Okay, so that's the model. And of course, the big question is, okay, have I thrown the baby out with the bathwater? If I simplified it so drastically that this has none of the physics that I'm interested in, that's a matter of opinion to a certain extent, but I should give you evidence that this model has pretty much all of the features that I very somewhat judiciously chose to emphasize in the experiments. Okay, so first question you might ask, why bother putting in so much randomness and all-to-all couplings? Well, there's various answers to that. One is that actually in the real system there is randomness. Okay, so okay, great. And then even though we put in randomness, at least in the part of the phases where we at higher doping and certain correlators in the spin glass phase, the randomness is self-averaging. The Green's function is the same on every side. So it's not as if you have some strange random-like features like many body localization or that kind of thing going on. That's just totally absent in this system. Even Anderson localization, every site is the same. Okay. And as we'll see, we can define small and large Fermi surfaces even in the random system. And I think many people agree that the essence of the physics is this Fermi surface transformation, how you go from a small to large Fermi surface. And so that key feature we won't throw out, so which is a good thing. But we will throw out some things, but let's assume those things are distractions, like charge density wave order, all other types of competing orders that people have been talking about. Well, generally, those orders appear at rather low temperatures, 100 Kelvin or below, whereas this pseudo gap Fermi surface transformation is already evident at 200 and 250, 300 Kelvin. So that's quite reasonable that if you want to only interested in this these higher temperature properties, which are still much lower than the natural energy scale of the system, then maybe it's good to work in a model where you don't have all these other distractions. And finally, we can numerically, so in the end, we're going to study, even this problem is too hard to solve exactly. We're going to study it numerically. So then you say, why not just study the real thing numerically? Well, of course, people have been studying the real thing numerically for 25 years. And there's been limited progress, partly because the system sizes are too small. You get all kinds of things happening, which depend on the geometry of the sample, and you can't really sort out what's going on. But in the random system, we can study much bigger samples, but we have this advantage we can average over thousands of samples. And once you do that, you get a very, it seems, smooth approach to the thermodynamic limit. And that's actually a big advantage. Okay. All right, so here's some results. So what's computed here is the energy distribution function of the electrons after fully diagonalizing the system. So what is this quantity? Well, this is perfectly the analog of what you call n of k in a Fermi liquid. You have, number of particles, momentum k, and in a Fermi liquid that has a discontinuity at the Fermi wave vector. That tells you where the Fermi energy is. Even in an interacting Fermi liquid, it has this discontinuity given by the quasi-particle weight. So how do I define that in a disordered system? Well, the idea is that there are quasi-particles, and if present in a disordered system, the quasi-particles won't be just plane waves. They'll have some complicated wave function. So what you should really do if you want to compute n of k is you assume set of quasi-particle wave function or quasi-particle state, which I call lambda. This is some single particle wave function lambda, and then you project with energy e sub lambda, and then you project your density matrix, single particle density matrix between sites I and j onto this quasi-particle state. And then look at how this varies as a function of E. And if you had the right quasi-particle wave function, you would see a discontinuity at the Fermi energy. Okay. Now, the remarkable thing about this model with all-to-all couplings, because of its self-averaging nature, you can actually prove that these quasi-particle wave functions are exactly nothing but the eigenstates of Tij. So the free particle wave functions do not get renormalized into the quasi-particle wave functions. And that's, roughly speaking, that's because the self-energies are all completely local. So therefore, you actually know what the lambdas are, and you can compute this N of E. So you get a Fermi energy. So these are N of E. Okay, we don't quite see discontinuity, but you clearly see some inflection points. And so you can then read off from the numerical data where you think the Fermi energy is. So here, as a function of doping, we plot the estimate of the Fermi energy from these plots from the expected value by the Latency Theorem. And what you find is that up to around 0.5, 0.4, it seems to obey the Latency Theorem. So there's a large Fermi surface present right there. And then once you go below 0.4, there is no large Fermi surface. We don't know what's going on. The distribution function doesn't seem to have any obvious discontinuity. Okay, so we found at least something we were looking for. We found a Fermi liquid at large doping, and then seems to disappear at low doping. So what is going on at low doping? I think I already told you this in my first lecture. So what you can deduce what's going on in low doping by computing the spin spectral function. Yes, Ngok.
So yeah, here, so this system, because of randomness, we don't have a momentum basically, and then
yes,
discontinuity is always a problem. And the way you suggested is that basically use this density of state, but what is delta EF? So basically, maybe my question is that the y-axis on the right here.
Okay, so there's several questions. There's a first, let me say, in general, for a disordered system, this would be impossible to do. Well, you could do it in some perturbation theory, but impossible to do exactly because the concept of quasi-particles doesn't really require momentum conservation. But if you look up the definition of a quasi-particle in any book, in condensed matter physics, it says, well, you look for a pole in the Green's function at fixed momentum. Well, if you have disorder, there's never any pole in the Green's function, no matter how weak the interactions, or the average Green's function. So therefore, excuse me. However, we still believe quasi-particles make sense even in a disordered system. It's just that the quasi-particle state has some random wave function. And it's very hard to, you have to solve the full many-body problem to figure out what those wave functions are. It turns out that in this special problem, because of the all-to-all coupling, because every site is coupled to every other site, and because of the extreme self-averaging, we know the wave functions, and these are the wave functions here. That's the beauty of it. So you know which correlator you have to look for to find the pole and to find the discontinuity in the Green's function. Okay, so what's the vertical axis?
Yeah.
So the vertical axis is you find the Fermi energy using this distribution function on the numerical diagonalization. So in units of t, it goes from between -1 and 1. These x points of the Fermi energy. And then, because we want to correct for finite size effects, you take just the Tij model, just take free fermions. And then also find their Fermi energy for the same, everything exactly same doping and so on. And this is the difference in the, now that Latency theorem tells you that two Fermi energies should be the same, which is the same as Kf in the momentum space case. Kf should be the same between the free fermions and the interacting fermions.
Yeah.
So here it's the Fermi energy that has to be the same by Latency theorem. And we do indeed find it's same up to some point.
I see.
Thank you. Okay, so that at low doping, what you have by computing the dynamic spin susceptibility is a spin glass state. And the spin glass order parameter seems to vanish around the same point that the large Fermi surface appeared. Okay, so we have then a conventional spin glass state at low doping, which, as I showed you, there's some experimental evidence for. And we have a Fermi liquid at large doping, which also there is experimental evidence for. What about near the critical point? What's going on? Let's see. So we can look at, say, the gamma value of the specific heat, and that has a nice peak, right, around the same doping, just like the experiments. We can compute the entropy. That also has a maximum, and there's no sign of a zero temperature entropy. I mean, but it's hard to be really certain from the system sizes we have. The entanglement entropy also has a maximum near the critical point. But what about Planckian behavior? Okay, so let's look at this dynamic spin susceptibility. So this peak here, I said, was the spin glass order. And as you increase P, then let's look at, say, the near the critical point, which is the red line here, this line over here. So it's got kind of a step function and then something that goes down linearly. And the brown line here, which says large M, is the exact solution obtained numerically of the Jij model that Jinwoo and I first solved. So the SY model. That is the numerical solution of it. Rescaled to set the value of J is slightly different, but it seems to match it extremely well. So more importantly, this behavior, chi double prime omega sine omega 1 minus psi omega, is in fact universal to the theory I presented in the first part of my talk. The sine omega is a consequence of the 1 over square root of omega behavior in the single particle Green's function. And this C gamma omega, this is the same gamma. This comes from the Schwartzian. So if you look at the corrections, so this we did not know before Kitaev's work. We can now figure out from the Schwartzian what is the first correction to chi double prime omega. It's linear in omega, as you see quite easily from the numerics of both the actual Syk model, but also this TJ model, which is far more physical, of course. In fact, in recent work with Maria and Grisha, we've got all kinds of other corrections that you can get using everything we know now about the structure of the Syk model. And also, if you could do this at finite temperature, yes, Inguk, I see your hand. If you could do this at finite temperature, then we see in addition this Planckian time appearing. This is an analytic calculation, not something that we tested for this TJ model yet. Yes, Unguk.
Yeah. So the what is this funny exponent?
This C. This C.
That's also interesting, and the exponent 2.7735.
Yeah. Yeah. Okay. Great. So the C is a number that you can compute. It's a universal ratio, and you can look up the number in our paper. So basically, there's the leading irrelevant operator is the Schwartz time reparameterization, and that has a scaling dimension which is fixed to be 2. Because it's fixed to be 2, this correction is integer powers of omega. Then there's a second leading irrelevant operator that has scaling dimension 3.77354. It's a solution of some transcendental equation. And in fact, there's an infinite set of these primary operators with transcendental scaling dimensions. And just numerical solution of those sigma equals g cubed equation I showed you actually shows all of these terms. It's really quite amazing how well that works out. C prime is another number we have to get numerically.
That's not universal.
No, gamma is not universal either. But for each irrelevant operator, there's one universal, non-universal number. Okay.
I also have questions. So if I have like Crick or Syk model, then would it change the powers?
Yes, it would, except the leading power. This is the same in every one of them.
I see.
But some of the others will change.
I see. Thanks.
Yeah, the short chain is present in every one of them. That's the key thing. All right. Okay, so here I want to show you some new upcoming results by the group at Flatiron, who's looking at the same model by a different method, by solving EDM-FT equations of that have been people at Flatiron and others like Vlad are experts at solving. It's not quite the TJ model, but it's pretty close to it. And this is their phase diagram as a function of temperature and density. And just like in our exact diagonalization, they see the spin glass metal, they see a Fermi liquid, but they're also able to figure out electron lifetimes at finite temperature. And very beautifully, they see linear NT behavior and also breakdown of the Latency theorem as you approach the critical point to the onset of spin glass order. All right, so that's a summary of the results of this numerical work. The random TJ model has spin glass order for P less than PC. It's a Fermi liquid with a Latency volume Fermi surface for P greater than PC. Maximum and entropy, specific heat, and entanglement entropy near P equals PC. And in the numerics, pretty good evidence for this kind of Planckian behavior near PC. And even some evidence in this TJ model for this universal graviton correction. So that's pretty amazing that this SE2 model with no other, just the TJ model has some kind of holographic connection explicitly in this boundary graviton. Okay, so that's what we see numerically, but it is not something, as yet I haven't given you explanation for why, in particular, these last two features appear. And the honest answer is we don't fully understand it, but we have some ideas which I will share, and that'll be pretty much the end of my talk. All right, so the last part, we can't solve this SE2 random TJ model. Even with all its simplifications, it's too hard to solve. But there is a model we can solve, and it's basically a model where you take the SE2 and make it SUM, and then take the large M limit. This is pretty much was the original model that the SY model that we solved in '93, but now you dope it. Okay, so unlike the SYK model, when you take this limit, you get a new feature, and that turns out to be really crucial. And the new feature is fractionalization. So this is what I talked about yesterday. So to understand these results, I claim you have to combine two pieces of physics that I've talked about so far. One is the SYK physics, and the other is the physics of fractionalization and deconfinement. You need both to understand this random SU2 TJ model.
Subir, can I ask a simple question?
Yes, please.
So for this random TJ model, even we are a little bit away from the P critical, so then we have this quasi particle, or
Well, I would say we don't know. I mean, this is
Uh-huh.
numerical data. You can, up to size about 20. That's the biggest sizes we had, 18 to 20. So you can see the data. We can't tell you the critical point. It's somewhere between 0.3 and 0.4. It's hard to say better than that. Everything. The accuracy is not that great.
I see. Thanks.
But the fact that there's two phases with some Planckian criticality in between, we can see quite clearly. But are there three phases, or is it two phases with one critical point? We can't tell. There could be a critical phase in between. I think that's one of the open questions.
I see.
In the large M theory, you actually get a critical phase.
Thanks.
Okay, Hanbit, maybe you can also ask question now.
Thanks. I have a questions about, you briefly mentioned about random TJU model. So if you introduce the, how about the U term, then is the Anderson type localized states possible in the random TJU model?
No, because the TIJ, there's no sense of local space even. Every site is connected to every other site. So it's not as if some sites can just decouple from the other sites in some local region. There's no local regions. Yeah. They take a pretty large U. So you may as well think in their model they're looking at the U equals infinity. The reason for introducing a finite U in their model is just technical. Somehow they have developed some very sophisticated methods of conquering the sign problem. So they do imaginary time Monte Carlo. So all of this stuff that Plata and people are such experts at works better at a finite U rather than an infinite U.
Yes, thanks.
Okay, so now I'm going to give you a guess as to what's going on. And as I said, the key ingredient that's been missing is to, you have another question, Hamid? No, okay. Is to introduce fractionalization. All right, so this is work, actually earlier work with Darshan Joshi and Grisa Talapalsky, another student, Chen-Yuan Lee, and Antoine Georges. Okay, so this is the random TJ model again, but we're going to now solve it by this parton method. So we have three states, empty, up, and down, and we're going to say that. So one way of describing the three states is that we have some parton, a boson, which describes the empty state, and a fermion, often called the spinon. This would be called the holon. The spinon is a fermion, and it describes the spin up and spin down state. Then the electron operator, you can see, if you annihilate an electron, you create a holon and you annihilate a spinon, and similarly for the creation operator. The spin operator acting on these states is just F dagger F. You have this constraint that F dagger F plus P equals 1, and that induces a U1 gauge invariance. Okay, so one perspective that's very useful here is to think of these three states as the states of a superspin, which is in this SU1/2 superspin space, because there's one boson and two fermions. That's the 1 and the 2. So this is the slash separates the fermionic from the bosonic from the fermionic directions. So it's sort of like the group SU3, but it's SU1/2 because some of the commutators become anti-commutators. All right. So this is, I could rewrite the Hamiltonian using these holon and spin-on operators, and it's if you solve the theory exactly, I haven't done anything. It's just the same theory. Conversely, I can also do it the other way around. You can make the holons a fermion and the spin-ons a boson, and this will give you the group SU1/2/1. It's all exactly the same. And fortunately, if you open up your book on supergroups, it'll tell you these two groups are the same. Okay, good. So nothing has changed. Where we put the statistics doesn't matter. Okay. So now the important thing to note is when you put this in here, more crucial thing happens. Let me show this here. So if I put the C, you notice is a bilinear of these operators. So this thing becomes not a two operator term, it becomes a 4 operator term. And so does this is already a 4 operator term. So both terms become like Q equals 4 SYK terms. And that's the key thing now. So even having a Tij, it does not, provided you have fractionalization, gives you the possibility of getting a non-trivial critical state. That's roughly speaking why fractionalization is important to get something like the real world. All right, so as I said, both the Tij term involve 4 single particle operators. And now when you take the large N limit, you get saddle point equations, which are here, which are very similar to the equations that I started my lecture today with, except there's 2 types of Green's function, the fermion and the Poisson Green's function. Okay, so we've written many papers solving these equations. I won't bore you with any of the details. They're rather similar to the structure of the SYK solutions, but there are solutions not for the physical, for the electronic Green's function. There are solutions for the spin-ons and the holons. All right, so what
question?
Yes.
So usually when I do the partons, I introduce the internal gauge field to encode the constraint. And I guess because it's a 0-dimensional problem, so you didn't introduce the gauge field, but maybe I can introduce
there is a
field
gauge invariance,
right?
no doubt. I mean, all of the equations have this gauge symmetry. But in the large N limit, you don't have to explicitly introduce the gauge field, but you are not breaking the gauge symmetry. And it turns out when you look at the fluctuations, we haven't fully done it, but you will probably have to worry about a time dependent. The time component of the gauge field will give you additional 1/n corrections here that will not be present for the case of the pure SYK model. So there are some corrections that would appear at order 1/m, which will involve this gauge field.
I see.
You just only have the time. Sorry.
The trick is the large N limit, where the gauge fluctuations is not much important, but just the meta field. I see.
That's just exactly the same way in any, in any parton T of spin liquids. It's very similar. Okay.
Yeah. Thanks.
All right, but you get equations which are, these equations, SYK-like, rather than getting, mean field equations that you get that gives you the flux phase or something, for example, for the spin-ons. Okay, so these equations, we haven't, they're still quite difficult to solve, especially in the regime where the boson could condense, and that can happen even in this theory. And we haven't fully numerically resolved all of that. But let me just give you a rough picture of what you get. So what you find is that there's at least a finite window of parameters where there's an SYK-like solution. But this is an SYK of fractionalized excitations, not of electrons. And consequently, the electron Green's function is not 1/square root of tau, but 1/tau. And this is, in fact, what's seen in the numerics. And the spin correlation function is 1/tau, which is also great because that 1/tau is precisely what's responsible for this sine omega, the fact that there's a discontinuity at small omega. That sine omega is just the Fourier transform of 1/tau. Okay. All right, so that's great. That seems to fit. All right. And you've noticed I've drawn this picture here where these 3 states are nearly degenerate. And that's roughly what happens in the large N limit. This is where you get this kind of solution, which is critical. And it's a phase I mentioned, but we're not sure. Maybe that's an artifact of the large N limit. All right, so what happens on either side? Well, and if these 3 states are equal, the critical point PC will be a 1/3. Which is not too far from what we see numerically. Okay, so what will happen as you just think of these states on any given site, and every site is the same because of model self-averages, on the left-hand side, the spin states are lower in energy, On the right-hand side, the spin states are higher in energy. So how would I want to describe these two configurations? Well, here, at least for SE2. So what I'm going to do is what I would want to do is to take the lower state and make it a boson. Because that's, when if you occupy the lower state, more particles in the lower state and condense them, you're going to gain energy. So you want to make the lower state a boson. So what does that mean? That on this side, you make your holons bosonic, and well, spin-ons are fermionic. Now, when this boson condenses, you break the U1 symmetry, the U1 gauge symmetry, and these F just becomes electrons. And so this is, in fact, just the Fermi liquid state, where the spin correlations will decay as 1 over tau squared, and you get Fermi liquid like 1 over tau decay of the electron Green's function. Conversely, on this side, you do the opposite thing. See, at this critical point, it's kind of, you can use either description. You notice there's a whole similarity of this to the story I told you in my very first lecture of the duality between fermionic and bosonic gapless spin liquids. There seems to be some signature of that here. And for SU2, we can explicitly prove some of this duality. And so here you want to make your spins bosons. And when these spins bosons condense, you're going to get a spin glass order because the bosons carry spin. And spin correlation function will go to a constant because of this condensate. So that's precisely a spin glass state. And you'll get holons, which are fermions, and the density of these carriers is P, not 1 minus P. And therefore, this is exactly a small Fermi surface state. All right, so there's a very simple way by doing the statistical transmutation between bosonic holons and fermionic holons of getting the two phases with the critical point, which is S1 K-like in between. Okay, so that's mostly a conjecture. It's supported by a lot of 1 over m expansion, a lot of RG arguments that I've not presented at all. But we don't know if this is exactly what's happening in the numerics yet. All right, so I think that's the end of my talk, pretty much. These are the properties of the TJ model I gave in the first part of my talk. And there's a partial understanding, I would say, of these properties by combining the two main topics of my lecture, which is fractionalization and SYK criticality.
Yep.
Okay, thank you very much.
Okay, so the session is open for questions, but maybe I can ask question first because I have also a question. So about the duality you mentioned, how far does it hold? Does it hold even like at the order of 1 over n too, or is it only at the large n limit?
Okay, so it actually holds for SU2. The large m limits are different for the two of them, but the two theories become the same for SU2. So now for SU2, you can ask, how do you prove anything for SU2? Well, in SU2, you can there's a certain weak coupling RG that you can do, and you can compute the RG equations using either approach. So I have not shown how to do that, but our paper in PRX has many pages discussing this RG, and you can get the same RG equation using either approach.
I see.
So the RG equation is exactly the same, and there's a fixed point that appears in the RG, which has properties similar to this large M solution.
Yeah, that's very interesting. Yeah, thanks.
Thank you. Yeah. I think this is pretty cute. I don't know if it's correct, but I mean, you have an explicit realization of something people have been qualitatively thinking about for many years. That really, at low doping, it looks like a bunch of holes, and at high doping, it looks like a bunch of electrons. And in the fractionalized variables, you have to use different representations. And how do you put them together? Well, in this infinite range model, we know how to do it.
I see. Good. Yeah. Unguk, maybe you can ask question.
Right. So here, so at the critical point, can I understand some symmetry is enhanced? Is or
No, it isn't. We looked for that. We thought there might be a supersymmetry there, but there isn't.
there isn't? I see. I
No,
see.
no.
Okay. Or also, so there have been some generalization to the translation invariant system of SYK, and so here, can you do that also? So this, and I think you, Sentinel.
We're trying to think of it. And we want to. So the original SYK model people have put into translation invariant models, but those are all models which become Fermi liquid at low temperature. You know, because once you put in linear hopping, then there's no hope of getting as critical behavior at low temperatures. So that's why I prefer to work with the TJ model with the fractionalization. It's also more physical. You know, those lattice SYK model, one way to say that they're missing their Martness. There's no Martness in them. there's no insulator anywhere, no matter how strong the interaction. But this model has an insulator. That's really the key. And we have to keep that physics in. That's why fractionalization is important also. So I forgot, what was the question? Yeah, so how do I generalize this to the lattice? If you're thinking about it, I don't know a good way to do it. I mean, how to connect this to the lattice. Obviously, that's the next step. Yeah, so I don't know.
Okay, the next is Sangjin and Hyungsoon and Yuki, and then Hanbit. Okay, Sangjin, you can ask a question.
Yes, and at the same page, is there any simple understanding of a difference in spin-spin, I mean, the correlations of weight difference between SYK and the disordered Fermi liquid case? 1 over tau versus 1 over tau squared.
You mean this over here?
Yes.
Yeah, when we can get these results, no problem. The 1 over tau comes from, well, I mean, roughly speaking, oops, sorry. So the spin-on, so there's this representation of, say, the spin as a F dagger F. The F obeys the SYK equation, so it's 1 over square root of tau decay. So the spin, which is the square of the spin-on correlation function, has the square of 1 over square root of tau, which gives you 1 over tau.
Okay, so I guess basic Fermion weight is different, you say.
The spin-on, I mean, so the spin-ons and the holons behave just like the SYK fermions in this model. In fact, this is the original SY model. That's it. The 1 over tau decay of spins was already in my very first paper on this topic in 1993. Didn't have any doping in that paper, but yeah.
Yeah, I was asking the question just because of the basic. Can you go to the same page? No, the next page maybe.
This one?
No, yes, there. I mean the basic. I see. C is 1 over tau, but F is different. Okay, thank you.
Yes, that's the key thing. C is FB dagger, and so that also becomes 1 over tau for the same reason. Yes. And the fact that these two exponents are the same, that's somehow related to the this supersymmetry rotation. You can rotate this to this by a supergroup rotation. Okay. But there is no real supersymmetry, but the exponents come out to be the same. Yeah, so that's, and this is very different from the C's of the SYK model that were a square root here. I think this is a much, my personal opinion, I think this is a much better way of connecting SYK to the real world by using models of holons and spin-ons rather than electrons.
All right.
Okay, Hyungsoon.
Hi, thank you very much for a very interesting series of talks. So is there an experiment that can exclusively test this random TJ model?
Well, I'll give the standard answer, maybe cold atoms. I don't know. No, well, I think I would say the random TJ model doesn't need any tests. The numerics that the Flytrend group has developed are pretty good, and I think with few more. Yeah, well, no, I shouldn't say that. I mean, you can do about 18 sites, and maybe somebody could build a cold atom or a qubit system with 100 sites. That would be beyond anybody's numerical ability. So that would be very interesting to do. Yeah. I guess you could take a high TC superconductor and put lots and lots of impurities and study all of these properties. I think, yeah, but as you can see, it already agrees with many of the properties of the cuprates.
All right, thank you.
Sure.
Okay, next is Yuki.
Okay, thank you very much. Well, thank you very much for the very nice, beautiful lectures.
Thank you.
So my question is very simple and something related with the question raised by Unguk. So my question is I think your random TJ model is a kind of infinite dimensional model because every sites are connected with each other.
Yes, yeah.
But I understand that the original your motivation came from the cuprates, and there are many people believe that the two-dimensionality is very important for the fluctuations and the kind of anyway.
Yeah.
So my question is, do you have any comments on the dimensionality? And if we believe your theory, then I think we can expect a similar thing even in 3 dimensions. So do you have any comment on that two-dimensionality in reality?
Yeah. So I mean, I did have this slide where I talked about various reasons to study the random model. So what is two-dimensionality important for? So it's certainly important for, say, like the Goldstone fluctuations of the antiferromagnetic order, and also the Goldstone fluctuations of the spin glass order. But that's a very low temperature property. We just want to see if there's a spin glass phase or not, and whether there's a small to large Fermi surface transition. I don't think dimensionality is that crucial for that. Now, as to your other question, could this be seen in higher dimensions? Well, in principle, yes. But the trouble with higher dimensions is that in higher dimensions, if you make a magnet, it's very, very classical. It doesn't have very little quantum fluctuations.
Mm-hmm.
You're always just in the analog of the spin glass phase. So you would have to find a higher dimensional system which are strongly magnetically frustrated and has spin liquid-like behavior.
Mm-hmm.
Like the pyrochlore, for example, is something that people are studying these days. Unfortunately, people have not been able to dope the pyrochlores, but yeah, I could imagine that in 3 dimensions, you had some frustrated pyrochlore lattice and you're able to dope it, you could get similar physics, I would say.
Mm.
Yeah.
Okay, yeah. And also I'd like to ask, maybe this is out of your scope, but is there any connection to the superconductivity?
Thank you. Well, that's a good way of putting it. I mean, so I guess I would say that this model has random Jij, but if you put in an antiferromagnetic Jij, which is non-zero, make the mean non-zero of the Jij, I'm pretty sure you get superconductivity. So yeah, so these models have superconducting instabilities.
Mm-hmm.
We several people have studied them already. We're also doing some work. I think, like I said at the beginning of my lectures, the actual superconductivity itself is not a mystery. What we want to understand is the parent state of the superconductor, the normal state, and then how it becomes unstable. But the actual nature of the superconductivity and what causes the superconductivity, at least in a qualitative sense, I don't think is a mystery. I mean, we all agree that it's a spin fluctuation induced pairing of some type.
Okay, thank you very much. Thanks a lot. I enjoyed a lot.
Sure.
Thanks.
Thank you.
Hanbit, please make it short.
Yes. Thank you for a very nice talk. I have questions about the strange matter part. So as you mentioned at the first, the key puzzle of the strange matter is it has a universal coefficient alpha, which is the coefficient in front of the scattering rate. So according to your theory, can your theory match the value of alpha, which is order 1?
So I think we're working on that. So this numerical result not yet published. In fact, I haven't even seen the paper myself. I just saw these slides. So this is computing the imaginary part of sigma as a function of temperature. So I think alpha is related to the slope here. I don't think I'd be very hard pressed to read it off from here, but I think there could be some. They have rather strange units. I think this is something this kind of work can look into and look at different models and see how universal it is. Yeah. So that's certainly a great question for future research. But it's promising, at least it's linear in T.
Yes.
Okay.
Okay.
Thanks.
Maybe one final comment. I mean, linear in T, of course, is the big problem. But what I should emphasize is that there are all kinds of mechanisms of linear in T, but it's usually almost invariably they are linear in T at rather high temperatures, where the resistivity is a bad metal, resistance is very large, about a HOE squared. And this is one of the very, very few calculations where you get linear in T down to very low temperatures. So that's why it's so interesting. Not just that it's linear in T, but also it's down to very low temperatures.
Thank you very much.
Okay, I'm done. Sure.
Okay, thank you for a very nice lecture. I should say I also enjoyed a lot. And Unguk wanted to make a closing comment for you and the audience. So I would like to pass my turn to Unguk. Yeah, Unguk.
Okay, thank you. And of course, yeah. So the final lecture is now over. I think it is now time to wrap up Sugiura's colloquium and lectureship series. I'm very grateful for Sugiura's effort to make these wonderful lectures and also answering lots of questions whose levels are very easy ones and very difficult ones. I don't know if you feel there are any difficult questions, but seems like the levels are very different.
No, the questions were great, and everybody caught on. I didn't, I couldn't. All the weaknesses of material were exposed, which is great. It was very useful. Thank you.
So, and also I want to thank all the participants since it was the first lecture series. The organization of this lecture series certainly will be improved in future. And the Sugiura's lectures will be uploaded to the web page soon. So if you want to receive the video link, please email me, or maybe you can go to Sugiura's web page. Probably Sugiura will upload these lectures. And also, if you have any comments to improve our lectureship series, please email me. I would be also grateful for any comments. So, Sugiura, thank you very much for this nice talks, and hope to see you again soon in person.
Thank you very much, Younguk and Gail and Kwan and Sangbin and everybody else. Great meeting you and all the great questions. Really enjoyed it. Thank you very much.
Okay, so now officially the lectureship is over.
Okay, bye.
Bye.
그 비디오는 따로 다운로드 된 거 보내드릴게요.
저도 했으니까 저 혹시 뭐 제게
문제가 되면 연락 주세요. 네.
네네, 저 필요하면 연락드리겠습니다.
네, 수고하셨습니다.
다들 수고하셨습니다.
수고 많이 하셨어요.
네.